1884. A deaf Englishman in a damp lodging in Camden Town opens James Clerk Maxwell's Treatise on electromagnetism and crosses out 16 of its 20 equations. The 4 he keeps are the 4 every physics student on Earth is now taught. His name was Oliver Heaviside, and you have never heard it. The Wi-Fi signal that reaches your phone right now obeys 4 equations written on a blackboard in every physics department on Earth. Above the blackboard, in chalk or in print, there is one name. The name is Maxwell. Maxwell wrote 20 of those equations in a notation almost no one could read, and then died in 1879 without simplifying them. The man who folded the 20 into 4, who invented the vector calculus that physics still uses to write them, who never held a salaried post, his name is missing. What you are about to learn is something the textbooks do not say out loud. The 4 lines they teach you are not Maxwell's count. They are an English telegraph clerk's edit of Maxwell, performed alone in a series of unheated rented rooms while his hearing failed. The same man, 2 decades later, would predict from first principles the layer in the upper atmosphere that makes transatlantic radio possible. Other men won Nobel Prizes using his prediction. He died poor enough that he could not afford the train fare to collect the medal Britain finally tried to give him. We are going to look at exactly how it happened. Oliver Heaviside was born in Camden Town, London, on the 18th of May, 1850. His father was a wood engraver. His mother had been a governess. The family was poor, the kind of poor where a third son shares a room with his brothers, and the windows do not quite shut against the winter. When Oliver was 8 years old, he contracted scarlet fever. He survived. His hearing did not. By the time he was a teenager, he was severely hard of hearing, a condition that would worsen across his life, eventually isolating him almost completely. He left school at 16, in 1866, and taught himself everything that came afterwards. At 18, he took a job as a telegraph operator on the Great Northern Telegraph Company's submarine cable, based in Newcastle. For 6 years, he worked the Trans-North Sea cable, and in his spare hours, read every paper he could find on electricity and magnetism. In 1874, his deafness made the job impossible. He resigned. He moved back into his parents' house in Camden Town. He would never hold another paid position for the rest of his life. In 1873, while Heaviside was still in Newcastle, James Clerk Maxwell, Cambridge professor, the man who had unified electricity, magnetism, and light into a single theory, published a treatise on electricity and magnetism. It was, and is, one of the great books in the history of physics. It contained 20 coupled equations in 20 variables, written in the cumbersome notation Maxwell had inherited from the Hamilton-Tate quaternion school, mixed with Cartesian components. It described every electromagnetic phenomenon physics had ever measured. It was almost impossible to use. Maxwell died in 1879 at the age of 48, before he could simplify his own theory. The 20 equations sat in the treatise for the better part of a decade, admired and unused. Most working physicists could read them. Almost no one could solve them. The treatise was, in the words of one contemporary, a book scientists kept on their shelves to look at, not to open. Between 1882 and 1885, in a series of articles in a weekly journal called The Electrician, Oliver Heaviside rewrote it. He stripped the quaternions out. He invented, independently, in the same years as the American Josiah Willard Gibbs at Yale, the modern vector calculus, the divergence, the curl, the gradient, the operators every physics undergraduate learns in their second year. He took Maxwell's 20 scalar equations and folded them into 4 vector equations. The same physics expressed in operators a working engineer could solve. Those 4 equations are the Maxwell-Heaviside equations. They are the 4 equations on the wall of every physics classroom on Earth. Gauss's law for magnetism, Faraday's law, the Ampère-Maxwell law. Heinrich Hertz in Germany, working in parallel, arrived at a similar 4-equation form around the same time, and physics fairly credits both men with the modern reformulation. The book stayed under Maxwell's name, the editor's name did not. While he was rewriting Maxwell, Heaviside was also inventing the mathematics electrical engineers still use today. To solve the long telegraph line problems his old employers were struggling with, he invented operational calculus. a method that treats the derivative as if it were an algebraic symbol that lets an engineer turn a differential equation into a piece of algebra and read the answer off. The pure mathematicians of his day attacked him for unrigor. The engineers used it because it worked. From the same work came what we now call the telegrapher's equations, the equations that describe how a signal travels down a wire, equations every cable in the modern internet still obeys. The Royal Society elected Heaviside a Fellow in 1891. They offered him the honor and nothing else. No post, no chair, no salary, no laboratory. He continued to live in his parents' house, then in a series of cheap rented rooms, then alone. His older brother Arthur, also a telegraph engineer, supported him financially for years. He was difficult to know. He could be vicious in print. He feuded for a decade with the Scottish mathematician Peter Guthrie Tait over the relative merits of quaternions and vectors. He won the argument. The vectors are everywhere. The quaternions are a footnote. In December 1901, the Italian engineer Guglielmo Marconi transmitted a radio signal across the Atlantic. The signal was the letter S in Morse code, sent from Cornwall, received in Newfoundland. The British scientific establishment, almost to a man, did not believe it had happened. Their reasoning was simple: radio waves travel in straight lines. The Earth is round. A signal sent from Cornwall toward Newfoundland would, by the time it had gone 2,000 miles, be aimed at the stars. There was no known mechanism by which the signal could follow the curvature of the Earth back down to a receiver. There was no known mechanism by which the signal could follow the curvature of the Earth back down to a receiver. In March 1902, the American electrical engineer Arthur Edwin Kennelly published the answer first. He proposed that there must be a conducting layer in the upper atmosphere, a layer of ionized gas that was reflecting the radio waves back down to the ground. Months later, working independently in England, Oliver Heaviside reached the same conclusion in a short article for the Encyclopaedia Britannica. The waves were not curving with the Earth. They were bouncing off a mirror nobody had yet seen. The hypothetical mirror became known as the Kennelly-Heaviside layer. 2 decades passed before anyone could test it. In 1924, the British physicist Edward Victor Appleton confirmed the layer existed. By sweeping the frequency of a radio transmitter and measuring how the reflected signal interfered with the direct signal, he proved it and measured its altitude, about 90 kilometers above the Earth. Today we call it the E region of the Ionosphere. It is the reason a shortwave broadcast can be heard on the other side of the world. Marconi had been right because Kennelly and Heaviside were right. In 1909, Guglielmo Marconi was awarded the Nobel Prize in Physics for the transatlantic transmission. In 1947, Edward Appleton was awarded the Nobel Prize in Physics for confirming the layer. The Nobel Committee does not award prizes posthumously and does not award prizes for theoretical predictions without experimental confirmation. Oliver Heaviside was eligible for neither. He spent the last 17 years of his life in a small house in Torquay, on the south coast of Devon, growing increasingly reclusive. He heated the house with gas jets. He painted his fingernails a deep pink. He refused most visitors. The Institution of Electrical Engineers, in 1922, awarded him the first Faraday Medal, the highest honor in British electrical engineering. He was its first recipient. The president of the institution had to travel down from London to deliver the medal personally, because Heaviside could not afford the train fare to come and collect it. On the 3rd of February 1925, Oliver Heaviside died in Torquay, aged 74, from injuries he had received after a fall from a ladder a few days earlier. The estate he left was small. He had no widow, no children. He was buried in Paynton Cemetery in Devon, in a grave that for decades carried no scientific inscription. By the 1940s, every physics undergraduate on Earth was being taught his 4 equations, under Maxwell's name. By the 1950s, the layer he predicted was sometimes still labeled the Heaviside layer in textbooks. Today, the joint name Kennelly-Heaviside survives mainly in specialist literature, the E region elsewhere. T.S. Eliot, in his 1939 Old Possum's Book of Practical Cats, the source poems Andrew Lloyd Webber later adapted into the musical Cats, used the Heaviside layer as the place where souls go after death. It is almost certainly the most quoted reference to him in popular culture. and one most readers have never connected to a man. The Wi-Fi signal that reached your phone today obeyed 4 lines, he wrote. When it had to travel further than line of sight, it bounced somewhere off a layer he predicted. He left school at 16. He never held a salaried post. He died poor enough that they had to bring the medal to him. They are still teaching his work. They have never been teaching his name. Case files on the people history forgot to thank. New cases every week.